this type of equipment is not going away. It is going to probably be more coming into what we do as normal equipment for heating and air conditioning.
Well, I mean, crack open an ECM fan motor and you find out really quickly that it's just an inverter.
It's a great example.
All right, misnomer 1, we've got electronic boards, ECMs, inverters. Do they introduce more problems than they solve? That'd be a good question.
This is a big topic of conversation. Let me say it that way first. So many contractors out there, and I'm not trying to point fingers or anything like that. Almost every HVAC service technician out there is very comfortable with working with standard technology that uses a permanent split capacitor, compressor, ECM motor, what it was referred to when I went to trade school, because it was a capacitor, run capacitor in the circuit at all times. Now, whether or not that machine has a start capacitor added to it or not, if it are stored in torque depends on the machine and manufacturing, or if it added a start kit was added. But I think they're very comfortable with start capacitors, very comfortable with run capacitors, very comfortable with contactors, standard equipment that's been built for as long as I've been in this business, all over 30 years. Now we have the introduction to more and more equipment, including all the equipment that GREE meant, all inverter driven, all circuit boards, it's all ECM driven fan motors, compressors, so on. So it poses to now where technology is advanced to more boards, ECMs, stuff like that. The question that James just, or not the question, but the misnomer that just came up was, is that introducing more problems than solve? I don't think so. I think it actually does a better job of protecting equipment. I think it does a better job of making sure the system is installed properly. One of these things that these controls do, everything that's attached to them, is it keeps it from damaging the equipment. It didn't have those safety features. Yeah, safety features. You have high pressure switches, you have low pressure switches, stuff like that on standard equipment that's been out there forever. But that's all they really had. They didn't have any other good safety features built into it to keep that compressor from having a burnout, constantly going out on overload and overheating the compressor over and over and over again and things like that. So in my opinion, in the grand scheme of things, ECMs and inverters have improved the longevity of the equipment and the function of the equipment without unnecessary damage to the equipment from lack of refrigerant and so many other things that the equipment does not function.
I mean, I think you make a good point as far as being able to protect itself. You know, I know we've seen quite a few times, you and I especially, with systems that didn't have, let's say, a low pressure switch, right? You know, you take whatever SEER equipment that was at the time didn't have a low pressure switch. You know, the filter gets clogged or the coil gets dirty or something like that, or you know, you've got no way to monitor whether or not liquid's coming back, or in the case of a low pressure switch, you know, it's out of refrigerant. Nothing would cause it to trip, like nothing would actually shut down the system. So it just sits there, pressure gets hot, overload goes out, cools off, overload kicks back in. You know, it just kept happening like that. And you end up with a permanently, you know, broken overload stuck open inside that compressor, and now you're swapping out a compressor. Exactly. You know, which always killed me is, you know, we would look at it and go, well, you know, we're saving so much money on not putting a low pressure switch on that unit. But, you know, what are you paying for, like, in terms of, you know, warranty on the compressor, that kind of thing?
But even the low pressure switches in today's design of equipment are more lost charges. Unless that thing is almost completely out of refrigerant, that low pressure switch ain't doing any good. So you can have a system completely really low on refrigerant, yeah, and still consistently overheat that compressor to the point of we actually get a compressor burnout, or like you said, the overload goes permanently stuck open.
Right. You know, which, speaking of an overload, our overloads are externally mounted. So if the overload were to trip over and over again and it finally go out, you can replace it. You know, that's just one of those little design things that, you know, became recognized pretty quickly. That would reduce overall failure rate. If you put the overload on the top of the compressor, now you're not replacing compressors with the overload stucco, you're replacing the overload instead. No, but going back to like the dirty filters, dirty coils, that kind of thing, that's something that regularly happens. All of our equipment has a way to monitor whether or not, you might have a possibility of liquid coming back, or it's got freeze protection built into it. So you don't, unless you've installed something completely wrong. You're not going to end up with a solid block of ice, foil, that kind of thing in your compressor will sit there, just swimming in liquid, washing all the oil out of the compressor and all the rest of that, causing at least reduced life. At least reduced life. So so although there are differences, you got the inverter boards, you got the electronic stuff, you got the, all that stuff. So much that's built in from a protection wise that'll help it to last a lot longer and continue to cool. You know, and on top of that, I like the fact that it gives me at least a direction to go in with an air code rather than hooking up a whole bunch of stuff to go find out what it might be doing, what might be wrong. There's also, I mean, the reason why this stuff gets added is also because of efficiency. We add inverter boards because of efficiency, ECMs, and all the rest of that stuff for efficiency. We found out. I mean, you can look at it this way if you'd like. If you're familiar with the M1 blower test, right, for SEER ratings, for efficiency rating, all that did was they chose a higher static pressure, which would be more common in the field. Because, previously they had tested it like 1 inch or 0.1 inches, right? 1 inches water column. Years ago, that was realistic. You could possibly have a duct system like that. But if you're running, if you got a 4-foot plenum or a spider box or something like that, you're not running on 0.1. You're going to be closer to 0.5. And one of the reasons why that changed was to have a more realistic thing. We kept increasing the the minimum SEER ratings and all that. Well, it turns out because we changed the way we designed our duct systems, we took those slightly more efficient units and made them probably less efficient than the previous lower efficiency units. Because you take a unit that was rated at 0.1 static pressure and then put it on duct system that's 0.5, is that going to be the same efficiency? No, obviously not. You had equipment out there that was discontinued because it no longer hit the minimum SEER ratings. So we had to make that adjustment. And one of the great things that we did, in that case, like with the Flex or with our multi-pro systems, is that we're able to get efficiencies out of them that you can't get, that you're limited on trying to get efficiency just from making a bigger coil or a more efficient fan motor. We can get efficiencies out of it by slowing down the compressor, that kind of thing.
Well, so let's kind of circle back here. I mean,
okay.
To the misnomer, right? Misnomer is electronic boards, ECMs, and inverters introduce more problems than they solve, which I think we're on board when we say here that I don't think so. I think it's improved reliability and efficiency, enhances the diagnostic tools. And so a lot of the tools that we have now, we have them for the mini splits, we have them for the multi-pro equipment, we have them for commercial BRF. We do have enhanced diagnostic tools that you can hook up these machines, and you can get a lot of this information from the machine and never have to put a set of gauges onto it at all. The machines do a great job of protecting themselves with the thermistors and the pressure switches and everything else that are in them. They have built-in air codes. Some people look at it as a negative that a machine has so many different air codes. But on the positive side, it has so many different air codes. Rather than the machine actually getting damaged, the compressor getting damaged, or like you were talking about, James, where the unit's freezing up, or a lot of these other things that can happen to these machines, we're improving that technology and keeping that from happening and having the machine go out on air code. But well before it even goes out on air code, depending on the problem with the machine, the other thing these things have a great ability of doing is running at a reduced rate. So in other words, it'll slow the machine down, still provide some cooling or some heating, and still stay online, even though the machine has a problem, right?
Mm-hmm.
So the homeowner end user is still going to realize, hey, this thing's not working right, but it's not dead in the water, right? So, I mean, I have an example I can give you. It was just recently, there was a multi-pro job that had 4 indoor units, and it wasn't heating very well. It was very cold inside the home. But the machine wasn't down. It wasn't out on an air code, but the end user knew the machine wasn't working properly. Inadvertently, what happened was, as they shut down some more of the heads, and never really shut them down, but just set the temperature to where that unit wasn't calling anymore, we quickly found that if we just left one indoor unit running, the machine stayed on and it worked. It heated. And it heated fairly well on that one head. Well, the bottom line is the whole machine was low on refrigerant because they had a refrigerant leak in the piping. But the machine wasn't out of refrigerant to the point where it wouldn't do anything.
Right.
Or actually throw it into an air code. Eventually, it's going to throw an air code. But during that run cycle, that's what I was getting at, is it'll slow itself down. It tries to save itself. So in a lot of machines, like if you're talking standard equipment, if you keep running that machine like that low on refrigerant, you're going to end up with a compressor out on overload. The machine's down. Now the overload cools off, finally resets, and it keeps doing that till we get to the point of, like we just talked about earlier, where you end up overload never resets. We got to replace the compressor, or we end up getting a burnout on the compressor, and now we not only have to replace the compressor, but we have a contaminated system on top of it.
Mm-hmm.
So whether it be a mini split or multi-pro, they both have those types of protections built into them with the thermistors and everything that are on them that keeps the machine from actually losing that compressor. Mm-hmm. The worst case scenario that we end up with here is no heat, the machine's out on air code. Once we find and fix the leak, we can evacuate the system, charge it back up, we're back up and running. There was no damage to the equipment itself.
Mm-hmm. Well, I think another good point, something that we came into more contact with, I guess, with our Flex system when it was introduced, a few years back, is that we were dealing in a hell of a lot more duct work, than what we had done before. And, we kept finding, not you guys are watching the video. Of course, you guys are great. But there are many folks out there that, would not set the blower speed, would not try to use a manometer. Yeah, wouldn't try to use a manometer to determine what their static pressure was, what their expected CFM should be, that kind of thing. And, what would have happened with the standard system when you don't set the airflow correctly is that you do end up with a cold coil. You end up with liquid, returning back. You do end up with those problems. And those problems may not manifest themselves until you have an expensive repair.
Right.
2, 3, 4, 5 years later. And what we found, because of these protections, they're going, hey, we keep having all these problems. Well, it was letting you know that you had a problem within a week of installation, within 2 weeks of installation. That's exactly what it was. And I understand that it didn't provide like that separation, between the day it was installed and then 2 years later. I totally understand that. I get that thought process, that psychological effect there. Totally get it. But at the same time, it let people know really fast. They're going out the next week, they're setting dip switches, and then everything was golden. But we saw that so much more, out of the Flex or the multi-pro ducted systems. We saw that pretty early on. Everybody seems to have gotten a heck of a lot better at doing that. Finally got some dust on the manometer, keeping extra 9-volt batteries on the truck, that kind of thing. But, once you set that up, that's really the biggest variable that you're going to have in a system like this anyway. So much of that stuff is done by itself. You're not having to install stuff like that. You're not having to do a whole bunch of setup stuff on these systems. But the one variable that you do have is that duct system. We don't know what it's getting put on. Think of all the duct systems that you've ever seen out there. You're trying to design a system that can fit every one of those duct systems. Well, you're going to have something that's adjustable, like a blower, No, the fact is, too, I feel the need to make this point as well, as far as electronics are concerned. When it comes to inverter boards and all that, GREE's been manufacturing inverter boards for 30 years, only until recently, in some cases for our competitors, they've started having some inverter-driven equipment. And, unfortunately for many people, that's their introduction to inverters, For many people, that's their introduction to communicating systems, for example. Is folks that have been doing it for a few years. They're buying like basically a kit from from a third party manufacturer and shove it inside an existing system, and then learning all kinds of lessons along with you, right? You're learning the lessons for them in that case. I tell you what, there's a brand right now. I'm not going to mention any names or anything, but there's a very high dollar, high end inverter driven system that's out there. Really nice controller. I mean, top of the line, absolutely cool, right? I don't have a problem with it. Totally get it. But they did see a spike in inverter board failures, and as it turns out, your inverter board stays hot for a little while after it stops cooling. Well, mini split manufacturers have known that for decades now. And what can happen, like if you got a mini split sitting on a rooftop somewhere or something, just because you don't have a call for cooling doesn't mean something's not going to happen, because we've got a built-in sensor on the inverter board, and the fan motor can come on and cool that inverter board off. So even after you run a cycle, if it's still hot, it'll run that fan motor to cool it off. I mean, these are lessons that were learned years ago, and in this case, this very high dollar, very brand new system, top of the line and all that, they're discovering something that, again, is a lesson that's 30 years old or more at this point.
Well, and I think, James, that if we were in a little bit different era right now, and we had the improvements in more and more mini splits being sold in this country, more and more of the multi-zone type units, whether it be a multi-zone mini split or even the multi-pro. Let's say that all that got more popular before our government actually phased out incandescent bulbs. It would prove a point real quick.
Yeah.
And I'm sure everybody on this broadcast has probably at least been worked on a heat pump or an air conditioner in the past that had, when they did have incandescent bulbs, and every time that condenser come on outside, the lights inside the house would dim, because we get this big, huge lock rotor amps to get that compressor started, and we put quite a load on that electric panel, which drops the voltage to all the light bulbs inside the house, and they all dim down for a second until the compressor is actually running. Then the light bulbs get bright again. Yeah, I can't believe, I got to believe most people on here have done them service calls, because the homeowner swears up and down there's something wrong with the air conditioner or the heat pump. But that's my point to all that whole example here is, that's one proof that's very evident that this machine's already saving you money, because when these machines start, they're not pulling that high lock rotor amperage. They're pulling very little amperage and slowly building up speed, which gets rid of that high torque, turn the compressor on, lock rotor amperage that we need, and unnecessary use of power. So right there alone is just one little simple example of, what ECM and inverter driven units have done for this industry.
Right.
Supporting commercial equipment for a short period of time, when you talk about VFDs, and when they take a belt driven blower that is literally you, and I'm sure you all have heard it, you're walking through Walmart and all of a sudden you hear that package unit come on, because you hear that belt squeal, and the thing's screaming at you. But if that had that VFD on there, you'd never hear that, because the VFD is just like an inverter driver. So now it's going to start that blower up nice and slow. You're never going to get that high torque on that belt and get that belt squeal. You'll never have that complaint again. Now, it doesn't mean the belt can't go bad and wear and stuff like that. Still need belt changes, but you're not going to get that squeal. Not at startup. And I know people listening to this broadcast have all heard that. So it's not just in mini splits, in the equipment that we sell. Inverter driven technology is happening in the industry all over. They're doing it in package units now, where they're using ECM fans. Carrier's got that Eco Blue fan. They got rid of the squirrel cage. It just goes to show you, as we evolve and we try to reduce the power consumption on the United States power grid, inverter technology is where it's going.
Yeah.
Which leads me into part of the reason why I wanted to have this whole discussion. That is the fact that going back when I first started being a technical service advisor, then over 14 years ago, I remember doing training classes, and I would tell these guys, we're talking about inverter-driven blowers, not inverter-driven blowers, but variable speed blower motors and stuff like that. And I can't even tell you how many times I heard from contractors out there, well, I don't sell those. I don't install those because, we have nothing but problems with them, so I just don't sell them. And I just haven't got into that. Well, my response to them was, if you haven't gotten into using furnaces and air handlers with inverter-driven, or not inverter-driven, I keep going the wrong way, variable speed blowers or ECM blowers, you need to start, because that technology is not going away. But the technology that I can assure you is going to go away is the PSC fan motors that you've dealt with your entire career thus far. The government had already put in that ban and slowly phasing out incandescent bulbs. I just knew it was coming. I knew they were going to phase out PSC fan motors, and they did. That's essentially what happened. Now, if you buy any new furnace, any new air handler, doesn't matter who the manufacturer is, you are not getting a blower with a capacitor anymore. You're getting an ECM fan. It's inevitable. It's inevitable that I believe that PSC compressors that's in standard equipment today are going to go away. What's going to happen is you're going to have electrically communicated motors in the compressors or inverter-driven compressors. That's where the technology is going.
Right.
So well, I mean, crack companies that I have in this whole thing is, guys, it's time to get on board and learn and understand how this stuff works. Because what I was taught in trade school is, if you don't know how it's supposed to work, how can you troubleshoot it? That's the encouragement that I have. Is start understanding the equipment. Walk up that mini split and open it up and see a board and not know anything about how to troubleshoot it. Because whether you're working on a GREE or you're working on any other brand, the basic philosophy to how that machine functions is the same. So embrace the technology, learn the technology, make yourself a better technician. That's my encouragement to everybody that's listening to the program.
Right. Well, I mean, crack open an ECM fan motor and you find out really quickly that it's just an inverter.
It's a great example. If you take that end valve off of a variable speed blower motor, and then you got a 3-wire Molex plug that plugs up the ECM to that motor, when you unplug that and you ohm that out, you're ohming out a 3-phase AC motor, no different than a 3-phase AC motor in a mini split that's actually the compressor.
Right. Yeah. Or if you work on a commercial rooftop, the 3-phase blower motor, it's no different motor-wise. It's so different. In fact, I mean, that's where all the fun stuff is happening in that module right there. That's why it's got basically a heat sink on the back of it and relies on the blower to be operating to keep the thing cool. It is an inverter board. That's all it is. Why they decided to do like a pulse width modulation signal or a whatever go into it rather than having an externally mounted inverter board to it, I'm not sure. I don't know why they did that, but I mean that's actually something that's been used for a long time. So I mean, regardless, if you've changed out it's like this, well, I mean, having to change out these boards, that's what I've heard that from time to time as well. Talking about changing out a board, well, I mean that's no different than changing out a defrost board. As far as changing out a board. But if you've got a bad blower motor and it's an ECM motor, chances are what you're changing isn't the motor itself. It's probably just the ECM module in the back of it. So I got a bad blower motor. Not really. The motor itself, probably all right. Now can you get an ECM module separately from it, pre-programmed and all the rest of that and put it in yourself? I don't know. Maybe it depends on the manufacturer.
It does depend on the manufacturer.
Okay.
Some only sell the whole kit caboodle, and some sell you just the module. I mean, it just depends on how it comes. But you're right. Those motors are driven on many different ways. They use pulse width modulation. They use, that's no different than what we have in our equipment, where you have a 5-wire fan motor, or you have a 3-wire fan motor. How that motor's communicated to come on is a little different.
Right. It could be a 0 to 10 VDC signal. It could be a, which is really cool because like years ago on a 0 to 10 blower motor, I used a 9-volt battery to give it a signal.
Right.
Determine what part was bad. It's pretty, pretty simple.
It's funny that you say that because a lot of blower motors back in the day with ECM motors, that's exactly how they had you test them. It was with a 9-volt battery. It was in their testing instructions for that ECM motor.
Right, which gave you, roughly 90%.
Right.
If you had a big enough 9-volt battery, you could just do it like that forever, right? Just let it run. Hey, Seuss.
I think I'm back.
Now. Yeah, man. Let's do it.
Okay. All right. So I just kind of want to piggyback a little bit back what Greg was talking about, the inrush current for the motors, PSC versus ECM. And we got ECM now that, slowly just starts ramping itself up until it gets to its full speed, its full output, whatever the program is in the ECM. Now we compare that to the PSC where, we get that pretty much the jolt to get it going to 100%. So it doesn't do that gradual. And really that's where you miss, you don't get the efficiency that you get out of the ECM motor. So those are really good points, what Greg had pointed out there. And I just wanted to address that. The inrush is definitely a lot lower whenever we're talking about ECMs.
That's why the lock rotor amperage on a contactor when you replace it is so important.
Right, exactly.
Those contacts in there have to be able to handle that maximum locked rotor when that compressor tries to start. Otherwise, your contacts are going to weld on a couple times if it's starting if you use one that's not rated high.
Yeah, well, I know Jesus remembers the ice storm we had a few years back down in the Dallas-Fort Worth area.
Yep.
When the power would come back on, it'd start blowing transformers.
It's too much.
Coming on all at once, you know. They probably did what I did, is remove the time delay, from the thermostat. but entire, brand new houses, these big giant subdivisions and all that. So they've got, that model on every one of those houses. And yeah, everybody come on at once, blow the transformer. They're like, they're sending out messages. Everybody needs to save power and blah, 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 and all that. I ignored that because, I had one of the most efficient systems around. So, I went ahead and ran mine. But yeah, my inrush current wasn't there. I mean, my inrush current for that compressor is going to be no different than my lights coming back on. My LED lights coming back on. Let me say that. So,
when I've talked about that in multiple trainings, to get back to it, and I even bring the question up a lot. Is the compressors that GREE uses in these machines, are they AC motors or DC motors? They're absolutely a 3-phase AC motor. What they're doing with the inverter driver is creating, from single-phase power, creating their own 3-phase signal to run that AC motor through that inverter driver. Okay, so, but collectively what that means then is you can also measure the amp draw to that compressor just like you would any other compressor. You put an amp probe around the wire and you measure the amp draw to the compressor. You can do that on each lead just like you would on any other 3-phase motor.
Mm-hmm.
And the thing that I talk about in that is, okay, so if you think it's locked up or the compressor's stuck, so many people refer to or think of locked rotor amperage as this really high amperage, which is the term locked rotor amps came from, because you had PSC compressors that truly had a locked rotor amperage rating, because that's the maximum amount of amps that compressor can pull to get it to start from a dead stop, right? Well, when it comes to inverter-driven equipment, they don't have that, as we talked about with a variable speed blower motor or an inverter-driven compressor. They start out very low amperage and slowly speed up. You can still diagnose that compressor is being locked up or not just by taking the amp draw to each wire. If we get some sort of an amperage, 1, maybe 2 amps on each wire, but the compressor never actually starts and runs, then you've got a stuck compressor. We're not saying that with this equipment you'll never get a locked up compressor again. That's not true. It's a mechanical compressor, just like any other compressor. They can lock up. you're just never going to see that true lock rotor amperage because the inverter driver board won't allow it.
Right. Well, luckily we've got methods for testing those boards. There's an example I like to use all the time in live classes where I just go through and describe, just basic inverter function, how you go about testing it. It seems to be, I like to use it every time I talk about something like that, unless it's like a purely sales-oriented training or something like that. But because it is something that sticks with people, it's not just troubleshooting our equipment, it's troubleshooting anything that's got an inverter board, real basic checks, like checking the DC voltage, the DC bus bar voltage it's got capacitors. It's got capacitors
Right.
like every other motor's got. That's the method that you're doing to check those capacitors. If you got one of those capacitors out, your voltage isn't high enough, it may not run.
Right.
Well, of course, what you can see sometimes is maybe the voltage isn't very high, but it runs anyway. There's a couple different things like that we see from time to time. And then you can check the diodes. Doing a diode check. That's actually what turns the motor. So it's just an additional check. Like in that case, it's like checking the contactor. That's what brings the motor on, right? So it's really, as far as adding those checks, it's just adding a handful of checks that you would do on any kind of inverter-driven system that you're doing, and you're adding that to your toolbox because your most important tool's between your ears, right? Well, hopefully it is, but it's just adding that tool into your tool belt in your head. It's really all it boils down to. And of course, working on stuff is a great way to in order to get experience like that. Don't forget the experience that you already have. Like when you open this thing up, you're like, I don't know what I'm looking at and all that. There's still a whole heck of a lot that's just like every other air conditioner out there. Like you still need some superheat, still need some subcooling, you still need all those things. Still need airflow. Oh my goodness, you still need airflow. If you've got poor airflow, it's something that people seem to find here a lot. During this time of year, or for the folks up north, it's been a few months now, but the folks down south, who maybe just now finding out, is that they start getting error codes on mini splits. When they go over to heating, it ran fine all summer. Well, airflow. First thing I would check, on a mini split like that, is just walk over and take a look at the filters. Walk over, take a look at that, at the blower wheel. It might be dirty, you might have poor airflow, and it trips out on an air code.
It's interesting you bring that up, that, you still have very much the same stuff that you have in any other heat pump or air conditioner. And I talk about that all the time. You still have your basic components in any basic refrigeration system. You got a compressor, you got a metering device, you got an evaporator, and you got a condenser. None of that's changed. That theory hasn't changed at all.
Mm-hmm.
What's changed is how we monitor the operation, what speed the compressor runs, what speed the fan motor runs outside, what speed the fan motor runs inside, how much refrigerant we're putting in that evaporator to load demand, put it that way,
Right.
What the room temperature is, what the actual set point is, all of that in a fully communicating system such as the mini split. That outdoor board is the main brain. It knows all of this data, and that's what determines how it runs.
Mm-hmm.
So if you have a piece of data, in other words, say a thermistor that's not reading properly, the board's getting bad data.
Right.
So the machine's not going to run properly. It can't be electrically shorted or open. You have an error code for that. But you can very much have a thermistor out of range that is causing an erratic operation.
Right.
It doesn't happen that often. These thermistors are very reliable. It ain't like we constantly changing thermistors. I don't think that's it at all. But you can have that one that is giving you erroneous errors.
Right.
I've even seen it on the multi-zone mini split where the range was so far off that one circuit would never function. The other circuits will function. So let's say it's the A circuit. For whatever reason, I can't ever get any cooling out of the A circuit, but B, C, D, and E work fine. And then when they do their checking, they find out that A circuit's got a bad thermistor in it, not electrically open or shorted, way out of range, that the board doesn't know what to do with it, so it never allows refrigerant flow to that head. The indoor fan runs, but your EV's outside in that condenser. It just never lets the EV open, lets it flow.
Yeah, I mean, it's like having a bad TXV. It's like having a bad sensing bulb, something along those lines. I mean, that's what it uses to determine what position it should be in. The EV is no different in that regard. That's why you have a separate set of thermistors, both inlet and outlet, for each one of those circuits.
That's right.
And it actually reminds me of another one. I never worked on a walk-in cooler before, and I don't think I have since. But, you know, sometimes just by chance. I had a boss that would take every single job. So I just, you know, and they're like, oh, you know, VRF, just go out there and do this walk-in cooler. I'm like, I don't know how to explain to you how that's not the same. You know? And I know every one of you have been in that position before. Like, what the hell do you think? Why do you think this is the same? You know? And he's like, oh, you can figure it out. I was like, okay, fine. So I go out there and I discover that the control voltage was high voltage. And I found that out with my hands. So that was a cool lesson to learn. So don't do that. But it was out of refrigerant.
Right.
You know, I mean, I don't know anything else about walk-in coolers, you know, and all the cool fancy stuff you might be able to do with them, all the bells and whistles that they have. But at the same time, I know it has to have refrigerant, you know. So I had to like look up, you know, how you charge it and all that, of course. But you know, I didn't it's just like everything else that needs to be cold. I mean, just like my fridge, you know, if anything else goes out on my fridge, I don't know what I'm going to do because, you know, they got a lot of bells and whistles now, right? But on the refrigerant circuit side of it, I mean, yeah, you can figure it out. It's just heating and air conditioning. All right.
Yeah, I just want to encourage people to, you know, the thing is, the bottom line here, and the reason, the whole point of this whole discussion is this is not going away. This type of equipment is not going away. It is going to probably be more coming into what we do as normal equipment for heating and air conditioning. What I believe is going to go away is what we've used to. So what I'm trying to get service technicians out there to realize is, hey, you know, this ain't going away. It's time to jump on board. Let's learn this. Let's understand this stuff so that when you get out there, you know, you got a good understanding of this equipment. I'm not discouraging anybody from calling our tech support team. That's what we're here for.
Right.
I'm more than willing to take those calls. We don't know it all either. You know, the only thing we just embrace it, learn it, and get an understanding how the equipment works, because it's going to make your life easier when you go out there to do that service call, because you're going to have a good understanding of how the equipment functions.
Right, and you get paid for what you know. I mean,
Right.
I hope that most of you get paid for what you know, more about what's in your brain, less of what you could do with your back or your legs or your, you know, shoulders and all the rest of that. If you get paid for what you know, going out there and learning it, like, you know, attending stuff like this, hopefully you're learning something here. You know, just adding that knowledge to it. You know, people pay for knowledge. Of course, if they don't, somebody else pays for knowledge. That's just the way it is. And you know, I mean, I can tell you a lot of things have changed over the years since I've been doing this, especially on the mini split side and all that. I used to know people that all they did was mini splits, and they got subcontracted out by every other company to go work on every type of mini split. And one guy I knew, I don't remember where he was from exactly, but it was, you know, somewhere overseas, you know, and that's what he grew up with and all that. He built his entire business based on working on stuff that people weren't familiar with. And you best believe he wasn't the cheapest guy around. You know he wasn't, you know?
And he probably had a very successful business.
Yeah, he's still going, you know. But yeah, I mean, get paid for what you know more, get paid more, you know, kind of like a positive cycle, you know,
Right.
because you're, I mean, I'll be real with you, you know, your legs for the young people, you know, your legs and your joints and all the rest of that stuff don't last nearly as long as your brain should. So if you get paid for what you know, maybe all the rest of that, you can go out for a walk or something, you know. To go get some exercise, you know.
You know, there's huge gains with the inverter driven equipment too, because what these things can do is a heat pump, and the amount of heat they can put out versus a conventional system is night and day.
Oh yeah, yeah. Well, no, I mean, the thing is, if you've got like mechanic friends, especially if somebody's been doing it for a long time, I mean, they'll be able to tell you that, when like fuel injection came out, there was a whole heck of a lot of people that didn't want to work on that at all. They thought it was a gimmick, all kinds of stuff. Then you had, at the time, it was mostly Japanese manufacturers that were doing fuel injection. Oh, who wants that junk, that kind of thing. And then you had, on the stateside, you had some manufacturers that were doing throttle body, which is like a kind of a mishmash of both type thing, did those exist anymore? No, it's all fuel injected now. The only thing I own that's not fuel injected is probably my very old lawnmower or like a wood chipper. But everything else that required some kind of fuel efficiency has fuel injection on it. So, I mean, that's just the way it is. I mean, I remember when people used to have signs up for autos that said, they only worked on domestic, right? That they only worked on domestically made models or whatever. Well, you don't see those signs anymore.
You're right. I never even thought about
what happened to those people. What happened to those people? Like,
Well, they had to jump.
Yeah.
They had to jump on board, otherwise they weren't going to have any work.
Or I don't work on fuel injection. Well, eventually you were going to run out of business.
Yeah.
Unless you start with classic cars or something, and then God love you. But if hopefully you charge enough for it. But every industry has changes like that, and I mean, fortunately for a lot of us, we didn't have a lot of changes up until pretty recently.